Fáilte roimh go léir. Tá áthasing an ócáidse chur ar siúl. I'm not going to go into Irish, but even though the person that this lecture is dedicated in honour of was a fluent Irish speaker, Lochlainn O'Raifeartaigh. Lochlainn was a professor at the Institute for Advanced Studies, Dublin, and he was one of Ireland's preeminent particle physicists, theoretical physicist, who sadly is no longer with us. He died far too young. And this set of lectures is each year part of the Irish theoretical physics communities. It was originally the Irish Quantum Field Theory meeting, which was set up by Charles Nash and Siddhartha Sen. The lectures associated with Lochlainn O'Raifeartaigh, who was a participant in the early years of that program, were part of the Institute for Advanced Studies, the Irish Institute for Advanced Studies, way of funding these meetings. So it's a great pleasure to have two eminent speakers this evening, and thank you all for coming. I'm going to start with the first speaker is Faye Dowker. She is a prominent theoretical physicist working these days at Imperial College London. She did her PhD under Stephen Hawking, and then she went, if I remember correctly, to, was it Fermilab? Fermilab, and from there to Santa Barbara, and from there to Caltech, and eventually back to London. And she has close ties with the Perimeter Institute in Canada. She is an expert on causal set theory. She is one of the specialists in the foundations of quantum mechanics, and she is on the board of the School of Theoretical Physics of the Dublin Institute for Advanced Studies. So without further ado, I will hand the mic over to Faye Dowker.
Thank you, Denjo, for that introduction, and good evening, everyone. It's such a pleasure to be here. I can't tell you, this is my first trip for years, and my first speaking engagement in front of, live in front of human beings in the flesh. So I can't tell you just how happy and thrilled I am. So I hope that comes across tonight, just how delighted I am to be here. It's also wonderful to visit again the Dublin Institute for Advanced Study. It is probably one of my favorite, if not my favorite place to visit to come and do physics. The atmosphere and ethos there at the Institute is one of scholarship for its own sake, the pursuit of knowledge for its own sake, and to the highest standard. It's a real jewel and gem in the world of science, of theoretical physics. So it's always my privilege and joy to visit there. So every student of physics at some stage is exhorted to read at least get hold of, if not read cover to cover, the Feynman Lectures on Physics. There are 3 volumes of it. The first volume is about quantum mechanics, and in that volume, Feynman refers to, Richard Feynman, the particle physicist, refers to the logical tightrope on which we must walk if we wish to describe nature successfully. And he means by that, he's been talking about quantum mechanics, quantum physics, and he uses this word logical tightrope. Now, my colleagues, so the question is, what did he mean by that? And any mention of logic, or the idea that one might be questioning logic, or perhaps analyzing it or even saying that we might have to abandon it in some way, it makes my colleagues very queasy, and some of them freak out and stop listening if I ever mention it. Okay, but I'm going to push it. And I think the reason that people feel uneasy and worried is that the idea that we might be giving up on logic implies to them that we're just going to be totally illogical. That logic is somehow the foundation, it's the thing we don't question. Right? It's got to be logical, it's got to be, that's one of the foundations of physics and of maths and of science. So we don't want to be illogical, certainly. So I agree with that, I agree with my colleagues. And that's not what I'm going to be proposing. So what is logic, if you think about it? So I want to, here's a sort of rough definition of what logic is. So logic, you can think of it as a set of rules for and I'm going to be talking about logic as applied to science, to physics and to quantum physics in particular. So you can think of logic as a rough definition. It's a set of rules for deducing correct statements about the world, the physical world, from other correct statements about the physical world. Okay. And I'm going to argue tonight, and at the end of the talk, you can tell me how well I did and whether you buy what I've said. I'm going to argue that quantum mechanics implies that we must abandon, not logic, but a particular set of such rules, and that we must learn to reason, still logically, but in a different way, when we're talking about the quantum world. So that's my aim for my talk this evening. So Feynman's comment about having to walk a logical tightrope appears in the book, in the first volume of the Feynman Lectures on Physics, after he has discussed a famous, iconic experiment called the double slit experiment. And interestingly, so I'm going to describe it now, but interestingly, the particular experiment that I'm going to describe was only done relatively recently. So it's been a sort of thought experiment for a long, long time in physics, but a really important and iconic one, something that people base their intuition about quantum mechanics, if you can call it. If anyone actually has intuition about quantum mechanics, it's based quite often on this double slit experiment. So what is that experiment? Okay, so in the experiment, there's a source of electrons. Call it an electron gun. So it's actually just a wire that you heat up and by running a big current through it. So the wire heats up and electrons boil off the surface of the metal wire. And then you can accelerate those electrons by applying an electric field from the gun to the right in this diagram. And the electrons will end up on a glass plate, which is coated with a particular substance, so that when the electron hits the plate, it gives off a small flash of light called a scintillation. So I've just described that by this little flash here. But in between the gun and this glass plate, there is a metal screen, which, if it was completely solid, would block the electrons. So the electrons can't go through this metal and reach here. But in the metal plate, there are two holes, two slits. So they're long, thin slits. And I've totally exaggerated the scales here. So this is some long distance, and the distance between the slits is really tiny. So this is a huge a cartoon of the setup of the experiment. So the electron gun gives off the electrons. The electrons, some of them just hit the plate and get absorbed, but some of them make it through one or other of the slits and makes it to the screen and causes this flash of light, the scintillation. And what you can do is you can keep a record of the positions on this glass screen of the scintillations. So instead of just forgetting where you can send electrons through one by one. So little flashes will happen here and there all over this screen, and you just keep a record of where they end up on the screen. So that's the setup. You can also do the following thing, which is you can block one of the slits. So just and keep the other slit open. And if you do that, then electrons will go through this single slit and make scintillations on the screen, and you can gather all the records of the positions of the scintillations on the screen. And with one slit open, this is the pattern, this is the type of pattern that you would get of scintillations on the screen. The scintillations are sort of roughly evenly distributed across the screen. So if you wait long enough, more and more scintillations will happen, and this pattern will just get denser and denser and denser. And there's nowhere on the screen that electrons can't reach. Now you can do the experiment again, but this time you open the other slit, so unblock the second slit. So now electrons can go through the first slit that they went through before, but they can also go through the second slit. So there are now two things that it can do. It can go through the left, this slit here, and it can go through this slit here, and you can gather the information, the records of the positions of the scintillations on the screen, and without knowing anything about quantum mechanics, without just thinking about these electrons as little bullets, you might suspect that the pattern of scintillations that you would find would be just the one with a single slit open, but just more of it, because there's two ways that the electron can go now: the original way plus another way. But in fact, what happens is you get this pattern. You get stripes of scintillations. So there are bands on the screen where you still get scintillations, like this, vertical stripes. And then in between these bands, there are so-called dark bands, where there are no scintillations. So the electrons, if we go back to where, with one slit open, there's nowhere on the screen that the electrons can't go. But with two slits open, suddenly there are places on the screen where the electrons can't reach anymore. They don't ever arrive in these dark bands in between the stripes. Okay, that's what the phenomenon that Feynman was referring to when he talked about a logical tightrope. I'm going to give you another example of the sort of thing that Feynman was referring to when he was talking about this logical tightrope. So this is an actual experiment that was in a science fair at the Perimetry Institute in Toronto, in Waterloo in Ontario in Canada. I asked for a picture of an interferometry experiment. So in this experiment, I'm going to draw a cartoon of it on the next slide, but there's a laser, it's a green laser, here, and we're looking, this is a bird's eye view of this tabletop experiment, so you're looking down on it. Right? And then there are these components of the interferometry experiment, which I'm going to describe on the next slide. Okay, so here's a cartoon of what that experiment is. So here's the source, the laser source, and you can tune the laser source to be so, the intensity of the laser source to be so low that it sends particles of light, photons, through this experiment one by one. So each photon from the laser hits this, which is sometimes called a beam splitter, sometimes called a half-silvered mirror. And 50% of the time, the electron will go straight through that half-silvered mirror. 50% of the time, the photon will reflect off that half-silvered mirror. So 50% of the time, the photon follows the red path. 50% of the time, the photon will reflect off the mirror and follow the green path. These two blue things here are just ordinary mirrors. So if the photon goes along the red path, it just reflects off the blue mirror here and goes down here. If it goes along the green path, then it reflects off this mirror here and goes along the bottom path down here. And then at this corner of the experiment, there's another half-silvered mirror or beam splitter. And each of the photons, if the photon comes down the red path, it can go straight through the half-silvered mirror, or it can reflect off the half-silvered mirror. And the photon along the green path, again, it can go straight through the half-silvered mirror, or it can bounce off, it can reflect off. And at the end of the experiment, in the bottom right-hand corner, here and down here, there are two detectors, and you can choose them to be detectors that detect individual photons and that register the photons by clicking, for example. You can set them up so that it amplifies the signal, and yeah, you can hear it, you can make it give you an audible click, so that I'm going to talk about detectors clicking. So if the photon that you send through this experiment comes along this path here, and enters detector 1 will give a click. And if the photon, the individual photon that you send through the apparatus, comes down here and enters detector 2 will give a click. And each time you send a single photon through this experiment, detector 1 or detector 2 will click, okay? One or other. And you can do a similar thing now with this experiment as you did in the double slit, which is to block off one of the possible paths that the particle can take. So I'm going to block off this green path. So if the photon reflects off this half-silver mirror and goes down here, then it reaches this barrier and just is absorbed, and it never reaches the detectors. So the only thing that the photon can do is go this way in order to reach the detectors, is to go along the red path. And when it reaches this beam splitter, you find that 50% of the time detector 1 clicks, 50% of the time detector 2 clicks. So you just send photon after photon after photon. Approximately half of them end up in detector 1, half of them end up in detector 2. So 50% of the photons make detector 1 click, 50% of the photons make detector 2 click. And now let's move this barrier and put the mirror back down in the corner, so that now the photons have two ways of going through the experiment. They can go along the red path, or they can go along the green path. But now the photons have two ways to go. What happens is that detector 1 always clicks, and detector 2 never clicks. So even though this red path, which is the one that when it was the only one that the photon could take, even though when there was only this red path for the photon to take, the photon could go into detector 1 or it could go into detector 2. As soon as you give it another way to go, the green path, it suddenly can't get to detector 2. It never goes into detector 2. It only ever goes into detector 1. Okay. Now, what's going on? And famously, a Brian Cox spoof that you can find on YouTube says, and I'm not going to try and do my Brian Cox accent, that's why I love physics so much, because physics is all about trying to work out what the bleep is going on. And even though this is a spoof, it's not the real Brian Cox. It's the kind of thing that Brian Cox probably would say, and all my physics colleagues here would agree. Physics is about trying to find out what on earth is going on. So what is going on in these experiments? In order to give you the language to talk about these phenomena, I'm going to introduce two concepts to you. And those concepts are event and history. An event, and they're intuitive, they're not complicated philosophical concepts. You'll have an intuitive feel for them. An event is something that could happen in a particular region of space during a particular time. And in reality, an event either happens or it doesn't happen. I'm going to give the example of weather tomorrow later on. Of course, it could rain. So rain tomorrow in Dublin is an event. It's in a particular place, particular duration of time, and in reality, it will either rain or it won't rain. So it will either happen, rain will happen, or it won't happen. So an event is a very intuitive concept to us. We use the concept all the time. History is a particular detailed way in which an event can happen. So rain in Dublin tomorrow is a rather, it's a kind of coarse-grained description of the weather. So it could be that it rains for just 5 minutes tomorrow, or it could be that it rains for 12 hours tomorrow. Those are different ways that it could rain. And we can make the detail finer and finer. We can talk about exactly how many raindrops fall. We can talk about also, we can add other information about the weather, like what the wind speed is. So a history is a particular detailed way in which the event can happen. Okay. So in our, I'm going to focus on the interferometry experiment, the one with the photons rather than double slit. So in our experiment, there are two events which are particularly interesting. One is detector 1 clicks, and the other is detector 2 clicks. So those are interesting events to us. And for each of those events, let's talk about the event of detector 2 clicking. There are two histories, two relevant histories, two detailed ways in which detector 2 can click. There is the history where the photon goes along the red path and then through the mirror into detector 2 and detector 2 clicks. And there's a second history, which is that the photon goes along the green path, bounces off the mirror, goes down into detector 2 and detector 2 clicks. So the event that we're interested in is detector 2 clicking, and the two histories are photon goes along red path and detector 2 clicks, photon goes along green path and detector 2 clicks. And quantum mechanics, from a particular perspective that was introduced by Feynman, tells us that for every history, there is a number associated with that history, and the rules of quantum mechanics tell you how to calculate that number. There's a number, and that's called the amplitude of the history. And if you want to calculate the probability of an event happening, then you must take all the histories that correspond to that event, all the detailed ways that the event can happen. You calculate the amplitude of each of the histories. You add up all those amplitudes. You have a sum of those numbers, and then you square it. And that's the probability. Now, you may say, well, who ordered that? I mean, why do you do that? Why are those the rules? Okay. And at our current level of understanding, no one can answer that question. There is no answer to that question. Well, why square it? Why not cube it? Why not take it to the 10th power? Why do you square it? This seems a very strange way to organize a theory of the physical world. However, if you do this, you get the right answers for predictions for events happening. And, in particular, in our experiment of interest, we're interested in the probability that detector 2 clicks. Quantum mechanics tells us that we calculate the amplitude of the red history, we calculate the amplitude of the green history, we add them up and we square that. And it turns out that the rules of quantum mechanics tell us that the amplitude of the red history is equal to minus the amplitude of the green history. So when you calculate the probability the detector 2 clicks, you're adding a number plus minus that number, which gives you 0, and then you square that number. So 0 squared is 0, so you get the probability 0. Now, this framework is often called the sum over histories, for obvious reasons, because you're summing this amplitude over all the histories in this event. And it's the way that Feynman thought about what one might call the foundations of quantum mechanics. And there's a very nice book called QED, quantum electrodynamics, and it's a write-up of some public lectures that Feynman gave in the 80s, and it's based on these concepts of event, histories, amplitudes, and probabilities, and he gives many examples of how you can understand certain phenomena using these rules. So I thoroughly recommend that book. It's an example of Feynman's mature thinking on quantum theory. So with this framework, this sum over histories framework involving these concepts of event and history, we can explore what Feynman calls the logical tightrope. Okay, so I talked about weather in Dublin tomorrow being an event, rain in Dublin tomorrow being an event. And what I'm drawn here is a representation of all the weather patterns for weather in Dublin tomorrow. And if you know what, if you're familiar with the term Venn diagram, then you can think of this as being a Venn diagram. Inside this rectangle, think of it as a box. It contains all these red stars. Each of these red stars represents a particular weather pattern for Dublin tomorrow, including the temperature, the number of raindrops, the wind speed, really fine-grained detail and information. Okay, so each of these, and there'll be many of them. I've only drawn a few of them on the diagram just to represent, just to give you the idea that there are all these different weather patterns in here. But within this collection of all the weather patterns in Dublin tomorrow, there's a certain set of them in which it's raining. Okay, so all of the weather patterns in which it's actually raining, they're all contained in this circle here. So this is the rain set, the set of weather patterns, set of histories in which it's raining. And in this circle, this is the wind set. So inside here, all of the histories are ones in which it's windy. Okay. So rain is an event. It will either rain tomorrow or it won't rain tomorrow. Wind is also an event. It'll either be windy tomorrow or it won't be windy tomorrow. And in each of the events, there's many ways that those events can happen. Many fine-grained, many histories of the weather. Now, from these events of rain and wind, we can make new events. So you can make combinations of events. You can make new events from old events. So in particular, we can make the event which is it's raining and it's windy. And that is the intersection of the rain event and the wind event. So in these stars in here represent histories in which it's both raining and windy. So they form a new event which we call rain and wind. We can also make the event which is rain or wind. So in each of these histories, it's either raining or it's windy or both. So this is the event rain or wind. And then finally, there's another, as an example, this is the event that it's raining, and everything outside, all of these histories here that are not in the rain set are histories in which it's not raining. So this is the not rain event. And in the world, so after time has passed, so the day after tomorrow, we will know which of these events has either happened or not happened. And each event will either happen or not happen. So let's say, for example, day after tomorrow, we know that, looking back, it did rain. So the rain event happened. I've lost some lines here. There should be a line under wind. Okay, so the wind event, let's say it didn't happen. And then rain or wind, well, that did happen. Rain and wind, that did happen. That did not happen. Not rain, that did not happen, etc. So every event either happens or it doesn't happen. And this is what logicians call a truth table. And you'll have noticed that we can't place ticks about whether an event happened or didn't happen. in any old way in this truth table, because if rain happened, if it did rain, then of course, then the rain or wind event happened because it rained. So therefore, in the history, it did rain or it was windy. It rained. If wind did not happen, if it wasn't windy, then it can't be true that rain and wind happened. So we could not put a tick here. The tick has to be here. So rain and wind didn't happen because wind didn't happen. And because it rained, not rain didn't happen. Not rain didn't happen. So we have to put the tick there. So there are certain rules of inference that mean that when you fill out this truth table about which events happened and didn't happen, there are constraints. You can't fill it out willy-nilly any way you like. So here's an example of a rule of inference. If X or Y happens, then X happens or Y happens. Actually, and vice versa. If X happens or Y happens, then X or Y happens. Okay, so this is a rule of inference. It sounds nuts, I have to say. Right? So if you were to read this, if you were to say this without writing it down, you would have to say, if X or Y happens, then X happens or Y happens, with those sorts of emphases and pauses, and it would sound really bizarre and strange, right? Okay, so an example of that is the one we've already seen. If rain or wind happens, if that event happens, then rain happens or wind happens. It's either rainy or it's windy, and actually vice versa. Okay, so all this it sounds like a tautology. How could this fail? How could you have X or Y happening, but not have X happen or Y happen? It seems not to make sense. It seems to be illogical. And you would never in real life, in ordinary life, it seems, make this distinction between X or Y happening and X happening or Y happening. Well, I'm going to have to ask you now to suspend your disbelief judgments at this point, because in this interferometry experiment, sort of confronted by this very surprising phenomenon that even though when you block off the green path, the photon can reach detector 2, but when you open the green path, the photon cannot reach detector 2. Faced with this strange phenomenon, it's often said in discussions about the meaning, what this implies for the real world, it's often said that the photon does not go on one path. It's often said that it's not the case that the photon either goes on the red path or it goes on the green path. So this rule of inference that if X or Y happens, then X happens or Y happens is now in doubt, because X or Y is the event detector 1 clicks, because it's the event red path and detector 1 clicks, or green path and detector 1 clicks. Together, they just make the event detector 1 clicks. So this detector 1 clicks is an example of an event like X or Y. So if detector 1 clicks, then we say that the event has happened. It happens. But it's often said that neither the history green and detector 1, nor the history red path and detector 1 happens. So it's a common claim in discussions of this interferometer experiment. It's a common claim in the double slit experiment that the electron does not go through one or other of the slits. That's just not the way to think about it. You cannot say that the particle goes through one of the slits or the other slit. Nevertheless, it does reach the screen. So a similar claim is made for the double slit. And this is Feynman's logical tightrope. You have to tread very carefully in order to, so you're denying a rule of inference, one that you make automatically, I claim. You don't even think about it. It would sound bizarre and illogical to deny this, but we often do deny it when we're discussing these phenomena, these quantum phenomena. Okay, so just to summarize, here's my diagram, my truth table about weather in Dublin. So rain happens, wind doesn't happen, wind or rain does happen, wind and rain doesn't happen, not rain doesn't happen, etc. These rules of inference, the ones that come naturally to you, the ones that you use without even thinking about it, without even noticing it, you remove those inverted commas without noticing it. These rules of inference are collectively known as classical logic. It's sometimes also called Boolean logic. And I know Boole is someone who is celebrated here in Ireland because, of course, he was in Cork. So classical logic or Boolean logic, this is the everyday logic that you use without thinking about it. However, in quantum mechanics, it's being suggested that we do not apply these rules of logic, that we can have this situation. We can have the green path and detector, should be detector 1 actually. Green path and detector 1 doesn't happen. Red path and detector 1 doesn't happen. And yet, green path and detector 1 or red path and detector 1, which is just the event detector 1 clicks, does happen. So this is not a classical rule of inference. It violates the classical rule of inference. So the suggestion is that there should be different rules of inference, not the Wild West of any old thing goes, but different rules of inference, quantum rules of inference. But what are they? So in order to answer the question of what they are, we need to investigate a little bit where these rules come from. In particular, where do the rules of inference that we call classical logic, where do they come from? What's the root of these rules of inference? Why is it so natural to us that we don't even think about them? They come, they're very intuitive to us. Okay. So I claim that the source, the reason that classical logic is our everyday notion of logic that we use without thinking, is that in classical physics, which is, if you like, our everyday experience, in classical physics, the world is one history. So here's our picture of all the possible histories for the weather in Dublin tomorrow. When the day after tomorrow we look back, then one of these histories will have happened, one and only one. So it'll either be this one, or this one, or this one, or this one. And when one history happens, you can prove the classical rules of inference because, for example, if rain or wind happens and the world is one history, then that history has to be one of the ones in the rain or wind event. So it has to be in here or in here. But then that history either has to be in the rain event or it has to be in the wind event. So the fact that the world is one history implies that that rule of inference, X or Y happens, implies X happens or Y happens. And you can show that it implies all the classical rules of inference. So for example, one of the classical rules of inference is that if X happens, then not X doesn't happen, right? Double negative. So if X happens, not X doesn't happen. Well, that's because, for example, if rain happens, then, and the world is one history, then it must be one of the histories inside the rain event. So it must be that one, for example, or that one, or that one. But that means that it can't be outside. So it can't be in the not rain event. So the not rain event doesn't happen. So the world is one history is equivalent to being able to use classical logic, the usual everyday rules of inference that we are so familiar with that we don't even notice that we're using them when we're drawing conclusions, when we're making arguments. So logic here is intertwined with an understanding of what the physical world is in classical physics. So in order to understand or figure out what logic or rules of inference we need to use when we're talking about the quantum world, we need to know what the quantum world is. Then that will tell us what rules of inference we need to use. So, we need to ask, what is the world in a quantum system? Can it be the same as in a classical system, one history? So can it be the case that the photon follows either the red path or the green path through the interferometer? Can it be that the electron follows one path through one slit, or it follows a single other path through the other slit in the double slit experiment? Can we adopt an interpretation like that, a worldview of a quantum system like that? The answer is no. And in order to make that deduction, in order to prove that the answer is no, you actually need to consider systems which are slightly more complicated than the interferometer and the double slit experiment. Those hint at something, but they don't actually prove that you can't maintain this worldview that the world in a quantum system is a single history. There are, however, systems where you can prove that you can't maintain the view that the world is a single history. And this is just a representation of an example like that, where the set of all histories is covered by events which have probability 0. So events that don't happen. So this event doesn't happen, and this event doesn't happen, and this event doesn't happen, and this event on the outside doesn't happen. So there's nowhere for a single history to be, because this doesn't happen, so the single history can't be in it. This doesn't happen, so the single history can't be in it. This doesn't happen, so the single history can't be in it. And there's only one other place it can be, which is out here, but that has 0 probability, so the single history can't be in it either. So it can't be a single history. So we have to give up this view that the world in a quantum system is a single history, and that because the world being one history is equivalent to classical logic, that means we have to give up classical logic when we're reasoning about the quantum world. But what do we replace it by? What's the vision? What's the worldview? What's going on? What the belief is going on in a quantum system? How do we think about it? And that's the question. In my opinion, it's an open question, and it's an active area of research for me and my colleagues. And we are being guided by a set of heuristics, hypotheses, if you like, which include a few that I've listed here. So the heuristics are that there is one world, so whatever this worldview is for a quantum system, the world in a quantum system is just one thing. There are no parallel worlds or multiple worlds or many worlds. There's just one world. In that one world, every event either happens or it doesn't happen, just as in the classical case. So that's maintained. An event with 0 probability doesn't happen. That's also carried over. That's the same rule as you have in classical theory. And we should ask for classical logic to be recovered for macroscopic events. So events like the weather in Dublin, those are macroscopic events. Events to do with tables and chairs, to do with galaxies, with macroscopic things. We should recover the ability to reason about them using classical logic, it seems. Or should it? Okay, so now I'm going to tell you something. It's kind of a joke, but it's also serious at the same time. So, this was taught to me by the theoretical physicist Raphael Sorkin, who's also someone who is well known in Dias and I hope that he'll be able to visit soon. And I thoroughly recommend that he's invited to give a public lecture because I think that would be super interesting. Okay, so Raphael taught me this joke, which is called the parable of the quantum pie eater. So the quantum pie eater goes to the pie shop and says, what pies do you have today? And the pie shop owner says, apple and blueberry. And the quantum pie eater says, okay, I'll have the apple pie, please. And the pie shop owner says, oh, I forgot, I also have cherry pie. And the quantum pie eater says, in that case, I'll have blueberry. Okay. So the joke is that it shouldn't matter whether or not there's cherry pie available for the quantum pie eater to be able to decide whether they prefer apple or blueberry. The fact that there's cherry shouldn't make any difference at all. But it does make a difference. The quantum pie eater changes their mind. Because there's cherry, the quantum pie eater now prefers blueberry over apple. Okay. And that is what electrons do in a double slit experiment. It's what photons do in an interferometer. They decide what to do depending on what choices they have available to them, even though those choices seem as if they should not make any difference. The fact that there's one route through the experiment ending up at detector 2 should not be affected by the addition of a second route through the experiment. But it does affect it. In fact, it affects it the most it could affect anything. It makes it completely impossible. So electrons and photons reason in this way, right? So the question is, what about us? It's kind of a joke, but sometimes when I tell people the joke, they say, well, I behave like that all the time. So the question is there a way to think about things which seem to violate our intuitions about logic, about ways to reason? Is there a way to understand that in a way that is actually not so crazy? That it's not as alien to us as you might think at first. So if you try to be sort of classically logical about it, it doesn't make sense. But if you are prepared to maybe interrogate yourself how you actually behave, then maybe it's something which becomes more familiar. And with that, I'll end, and thank you for listening.
Gurmila Mahagut Faye, and the floor is open to questions.
This experiment with the beam splitter, so it looked like the setup was actually pretty easy. Do you think there's any chance that those experiments might actually be performed at home soon? Or is the material still too... Because it would be really nice, for example, in a high school setting, for example, to actually show an experiment that actually shows how weird the world actually is. But I guess you need a single photon emitter for that. With any ideas whether that is doable?
That's a good question. I don't know. And maybe there are experts here who could answer that. I mean, this was done at a a science fair, so it was it was just done on a tabletop in the atrium. It didn't require any complicated setup. But I mean, to really see the photons going through one at a time, which is when it's most dramatic, then you would need single photon detectors as well as a source which you can tune down to to reducing to sending photons through one after the other. That's a good question. It would be fun. Yeah.
Thank you. Will multiple causally unrelated universes count as multiple worlds in your language?
I'm not sure how to interpret your question, but what I mean by one world is that the one world is this one. I mean, it's meant to be a denial of claims that there are multiple copies of ourselves in universes sort of parallel to this one. So that it means that that's not the picture, that there's just one world and it's this one, if that answers your question.
You showed us the slide of 100% for the red, I think it was. I don't know if you can bring that one up. Yeah, and not. Okay, so you said the beam goes in from the white, it hits the orange, it goes to the blue, and it goes down to the orange again, and then pops out to 100% on that side. And then you said you put another beam in without the green. You showed us one without the green beam going through. Yeah, so you blocked it off. And okay, so you send the beam through on the red, it hits the blue, goes down, and you get 50% and 2%. Now, did you do... Yeah, so did you do the same with the green?
Oh yeah.
Did you block off the red and do the same with the green?
Yes.
Okay.
Absolutely, you can do that too. So you can block off the red, let the green only have the green path available.
Yeah.
And that will also be 50-50.
50-50.
Yeah.
And then you said you put the green beam down onto the red and you got 100% in the one. From there. So if you've sent the beam through, right? You said 50% will go the red path on for the top orange one, and 50% will go the green path.
Yeah.
Right? So then they both hit the bottom, which in one length, and they go across the side, which is the second length of the square that you're talking about, and they hit the beam. So obviously, in the second case, the green one hits the red and sends it across to 100%. So there must be more power in the way it's going across, the actual, whatever's going across that microscopic thing. But also, the question is, did you ever move the blue mirror on the green down a bit so it's not a square? Did you ever move it so it's a quadrangle or something like that? And then see what would happen?
These experimentalists do all sorts of things. So they do also, this is the simplest thing that you could possibly do, but they add all sorts of components. So they can change these percentages by adding what are called phase shifters in here. And they can make these percentages anything you like. But what's not happening is that something is going along the red path at the same time as something is going along the green path. There's one particle, one photon, and it either goes, well, this is the intuition that one has, it either goes along the red path or it goes along the green path. And you can do an experiment where you put a detector, forget this bottom part of the experiment, just put a detector here and put a detector here. And then you send a single photon in here, And then 50% of the time that detector will click, and 50% of the time that detector will click. So send a single photon through, either this detector will click up here, or that detector will click. So that implies that when you send a single photon through, it will either go on the red path, or it will go on the green path.
But it also implies that it's a straight line, and it's not varying at all in height, or...
Sorry, I think we
they're
have to cut
lasers,
that
so.
discussion off. I think at this point there are some others want to get in. You can try getting in later. Okay.
So thanks for the very nice talk, first of all. But I'm very fascinated by this approach of logic in quantum mechanics. So because we're very used to ask correlations, like about correlations in quantum mechanics, are you implying that we should start ask causal questions and not just questions of correlation?
I'm suggesting that we should ask ontological questions, I suppose. I mean, the question, when one says correlation, you have to say, well, what's correlated with what? So in order to talk about correlations, you have to talk about something being correlated with some other thing. And the question is, what are those things? So there's something prior to correlation, which is what is being correlated. It's the prior question that is the one that well, I don't know the answer to it, so that's...
But you're now shifting to asking, does switching on beam green cause a different measurement? It's not just it's correlated, but it's causing that, which allows us to ask this logical question. And that's a theory about reality, because before we were talking about an observation. A is correlated to B, but A causing B, that's a theory about reality, it's not just an observation.
Cause is I don't know what cause and effect mean. I mean, so I can't answer your question because I don't know what cause means. I don't know.
Take one more question because we have another speaker.
Yes, thanks for the talk as well, really nice. So, it's a bit unrelated but also related. So, as far as I understand, you're an expert in causal set theory, right? Okay, so have you been able to derive I don't know how to put it, different kind of microscopic causality that has an effective limit, our causality or something like this? I'm not sure if it makes sense, but...
It makes as much sense of the sort of conversations my colleagues and I have, which I think the sorts of, exactly that sort of discussion or question. No, it's tied up with this, my inability to understand what causation means, I think. Well, thanks for the question. It's deep, deep.
Perhaps we can stop this discussion, and should we have 5 minutes break before we begin the next talk? What does our speaker think? Or
Ready to go on with what people want.
do people need a break? One person needs a break. Okay. Yes. Perhaps we will just continue so, right? So our second speaker this evening is Professor John Ellis. He is the Clerk Maxwell Professor of Theoretical Physics at King's College in London. He received his PhD from Cambridge University. He worked at SLAC, Caltech, and CERN, where he was the theory division leader for 6 years. I believe he moved to King's relatively recently, so he has been involved with the Large Hadron Collider at CERN, especially in Higgs physics, and was one of the early proponents of experiments to measure the Higgs, which was discovered relatively recently. He was awarded the Maxwell Medal, the Paul Dirac Prize, and he was elected in Fellow of the Royal Society of London and of the Institute of Physics, and is an honorary fellow of King's College, Cambridge, in King's College London, and I'm sure I've left many things out. So it's a great pleasure to welcome John Ellis to give tonight's second O'Raifeartaigh lecture. Thank you, John.
Well, thank you very much for that very kind introduction and the invitation. The only thing I hope is that I spelt O'Raifeartaigh correctly. Is that okay?
His son is over there.
Yeah, hi. So, my title is What Are We? Where do we come from? Where are we going? And this is the title, well, actually, the original was in French, of a very famous painting by Paul Gauguin, whom you see here. A bunch of people posing some very fundamental questions, almost as philosophical as Faye's questions, but perhaps not quite. And I want to convince you that the aim of particle physics is to try to provide answers to these questions. And if I want to sort of boil it down to one question, what is the matter in the universe made of? I should say that I came across this picture for the first time when I was a student, and I was in Boston. I saw the picture, I bought a copy, I went back to my office in Cambridge, and I put the copy on my wall just to remind me why I came into work each day. And it's still why I come into work each day. So, as was mentioned in the introduction, there's this famous particle called the Higgs boson that was discovered almost exactly 10 years ago. And what I want to do in this talk is to take you from the Higgs boson to the dark side of the universe. This is actually a picture of Peter Higgs in 1965, shortly after he proposed his theory. And if you could read that, you would see some of the secret details of his theory. Okay, so Gauguin's questions. So what do we know about the universe? Well, we see all these stars, we see all these galaxies, and one of Gauguin's questions becomes, what is the universe made of? What are the fundamental constituents of the matter in the universe? And as I'll discuss in more detail later on, a part of that is what is the visible matter in the universe, but there's also a question, how about all the invisible dark matter that astronomers tell us is out there? Where do we come from? So what happened 13.8 billion years ago when our universe emerged from the Big Bang? What were the fundamental physics processes that guided the evolution of the universe, which got us in the mess that we're in today? And what's going to happen in the future? I'm not talking about World War III. I'm talking about, will the expansion of the universe continue forever, or will it at some point go into reverse? So those are the big Gauguin questions from my point of view. So here I dig down a little bit and sort of put a little bit more detail into these questions. So what is matter made of? And a key aspect of that is why do fundamental particles weigh? Now, if, for example, the electron didn't have a mass, then there would not be any atoms, because electrons would just fly away from nuclei at the speed of light. So thanks to Peter Higgs, we now understand where the electron mass comes from, we think, and so he's allowed to smile. What's the origin of the matter of the universe? Where do we come from? I mentioned the dark matter. What is the nature of that dark matter that fills the universe? Where do we come from? Where are we going? How does the universe evolve? Well, it evolves according to Einstein's equations of general relativity, we think. But you have to put into those equations the right sort of stuff, the right sort of mass and energy. And that's linked to the question of why the universe is so big, and what is the future of the universe? Okay, so these are the things that I try to think about when I go into the office. And I would claim that answers to these questions need physics beyond what we currently know, And these are questions that are being studied in one way or another in experiments at the CERN Large Hadron Collider and elsewhere, as I will discuss. Okay, so let's just recap what we know. So we know that we are made out of molecules composed of atoms, which contain electrons in clouds around nuclei, that inside those nuclei there are things called protons and neutrons, and those protons and neutrons, they're not elementary particles, they matter out of smaller things called quarks. So as far as we know at the moment, the most fundamental constituents of the visible matter in the universe are those quarks and electrons and related particles. And they made Einstein and his kid sister. But astronomers tell us that there has to be something else, that the apparently empty space around the stars and galaxies, or around the galaxies in clusters, is not in fact empty, that there is some sort of invisible dark matter which does not interact electromagnetically. So what do we do with the Large Hadron Collider? Well, you can look at it simply as a supermicroscope, which studies what goes on, inside the atom, inside the proton, perhaps inside the quarks. But I would argue that it's more than that. It's not just a supermicroscope. It's also, in some sense, a super telescope, which studies the physics laws of the first moments after the Big Bang. And that gives us the possibility of answering some of the other Gauguin questions. So here is what we think at the moment about what happened shortly after the Big Bang. So in the universe today, as I said, we have stars, we have galaxies, we have atoms. But if you go back when the universe was less than 300,000 years old, there would not have been any atoms, just because the universe was too hot and too dense. Atoms would not exist, they would be instantly ionized. But then as the universe expanded and cooled down, atoms were formed, and when they were formed, they emitted radiation, which we see today as a relic of the Big Bang. And so that way we can actually, if you like, monitor the birth of the atoms. Now, the atoms consist of nuclei and electrons. But if you go back when the universe was less than 3 minutes old, it would have been so hot and so dense that there would not have been any nuclei either. They would have become sort of, if you like, nuclear ionized, and you'd have had just protons and neutrons as the fundamental constituents of nuclei. But if you go back when the universe was less than a microsecond old, protons and neutrons wouldn't have existed either. The temperatures would have been so high, the density so large, that protons and neutrons just couldn't exist, and you'd be left with quarks and the other fundamental constituents of matter. So those protons and neutrons appeared when the universe was about a microsecond old. If you go back to when the universe was a picosecond old, so a millionth of a second old, that's when we think particle masses appeared. That may be also the time when matter, or the dominance of matter over antimatter, occurred. It might also be around the time when the dark matter sort of decoupled itself from the visible matter in the universe. And please don't ask me what happened at time equal to 0, because I have no idea. Okay, so one of my theses is that there is this close connection, symbiosis between the physics of the very small and astrophysics and cosmology. And in fact, this goes back over 100 years to when Victor Hess discovered cosmic rays. So these are energetic nuclei and particles that come from some explosions out in the universe. And when those particles hit the atmosphere, their energy is converted into new particles. And it was in those collisions that in the first half of the last century, many fundamental particles were discovered. So I'm going to be talking later on, for example, about antimatter. The first antimatter particle was discovered in the cosmic rays. The electron, we know, is not the only particle of its type. There are heavier ones, and the first of those, the muon, was also discovered in cosmic rays, and so on. So around the middle of the last century, physicists realized that if they wanted to analyze those particles in detail, they would need to study them under controlled conditions in the laboratory. And that's why they built particle accelerators and colliders, so that they could study the particles and their properties under controlled conditions in the laboratory. Big laboratories, but laboratories. So what do those studies reveal? So they established something that we call prosaically the standard model of particle physics. This was proposed in 1967 by Abdus Salam, originally from Pakistan, and two American physicists, Shelley Glashow and Steve Weinberg, who unfortunately passed away quite recently. So their theory was first tested in experiments at CERN that found the first characteristic prediction. And then there were many much more detailed, much more precise experiments subsequently. And I used to write here, perfect agreement between theory and experiments in all laboratories. But my specialized talk this morning was devoted to discussing various anomalies that indicate possibly slight disagreements with the standard model. So I can see somebody smiling over that. Anyway, so I put in a question mark. So what does this theory contain? So it contains constituents of matter. So I've talked about the quarks, I've talked about the electron, I've talked about the muon, which is the sort of heavy electron, and there's a third one also. There are neutrinos, but I won't say very much about those in this talk. So these are the fundamental constituents of matter. And between them, we distinguish 4 fundamental interactions. So 2 of these are pretty familiar to everybody. Gravity, like things drop. Electromagnetism, lights shine. But inside the atom, there are 2 other forces. One is the strong nuclear force that holds protons and neutrons together in nuclei and holds quarks inside those protons and neutrons. And then there is the weak force, which is responsible for forms of radioactivity. Now, what's written on this slide is almost enough to explain all the visible matter in the universe, but not quite, because there's nothing here to tell you where the masses of the elementary particles come from. And that's an important loophole. As I already commented, if the electron didn't have a mass, you wouldn't have any atoms. Electrons would fly away from nuclei at the speed of light. This weak nuclear force would not be weak. It's weak because the particle that is responsible for it is very heavy. But if it didn't have a mass, then life would become impossible. So, we owe a lot to Peter Higgs, whom you see here, who gave us an answer to the question, where do the particle masses come from? Now, you might be a little bit surprised. You might say, well, I learned about mass in high school. Yes, you learned about mass in high school. And you learned that according to Newton, weight is proportional to mass. And everybody knows about E equal to mc squared. Einstein tells us energy is related to mass. But neither of these distinguished gentlemen got around to explaining where the mass comes from in the first place. So Peter Higgs is the man with a theory for that, and it is described on the blackboard behind him. And if you permit me, just in case you forget some details of the theory, I have it on my t-shirt. Right, now I've screwed up the audio system. Okay. And I screwed that up too. Okay. So this is the standard model, the fundamental equation that describes the standard model, makes all those wonderful predictions. Okay, so in this, there is something called phi. Phi is what we call a field. It's something which sort of exists, extends throughout all space. And you know of at least a couple of examples of such fields. There's electric fields, there's gravitational fields. The Higgs is a different type of field, whereas electric and gravitational fields have sources, and they're not the same throughout the universe. There's a stronger gravitational field closer to the sun, a stronger electric field closer to an electric charge. The Higgs field is something which is uniform, and as far as we can tell, constant throughout all the visible universe, isotropic, homogeneous. So I like to compare it to a snow field. Now, imagine, if you agree, that you're in the middle of Siberia in the middle of winter. Okay, so you've got this uniform field of snow all around you. Imagine that you want to cross Siberia. So you might be lucky and have skis. In that case, you skim across the top of the snow. You don't interact, at least not strongly, with that snow field. And that's like a particle, for example, the photon, that does not interact with the Higgs field. It travels always very fast at the speed of light, in the same way the skier travels very fast, because it has no mass. If you try to cross Siberia with snowshoes, then you will sink into the snow, you will go slower, and that's like a particle that interacts with the Higgs field and acquires a non-zero mass and always travels at less than the speed of light. An electron, maybe. Or maybe you don't have any snow equipment at all. Sorry, maybe you have no snow equipment at all, and so you're trying to walk through Siberia. In that case, you're going to sink very deep into the snow. You're going to interact very strongly with the Higgs snow field. You're going to travel very slowly, like a particle with a large mass. Okay, so your mass, or particle's mass, is proportional to how strongly you interact with that universal Higgs field. So then the question comes, what is that snow field made of? Well, you know the answer, it's made of snowflakes. The corresponding question for the Higgs field is, what is the quantum of the Higgs field? And that is the Higgs boson. So you can regard the Higgs boson as being a somewhat flaky theory. And indeed, back in 1975, it was regarded as being a somewhat flaky theory. And that's why when we wrote our study of the possible experimental profile of the Higgs boson, we were regarded as being slightly nutty. And we were a little bit cautious at the end of our paper. We said we don't want to encourage big experimental searches for the Higgs boson. Well, fortunately, that bad advice was not taken. And CERN built the Large Hadron Collider. So in a tunnel, 27 kilometers in circumference. You don't actually see it from the plane because it's buried 100 meters underground. And that device is, purpose is to at least try to answer Gauguin's questions. So here I've taken you down inside the tunnel. So these are magnets inside these tubes. And when the thing is operating, you've got thousands of billions of protons circulating in opposite directions. Each of them has, roughly speaking, the energy of a fly. And they make billions of collisions every second. And in those collisions, we set out to establish where particle masses come from, perhaps what is the nature of dark matter. We were going to study the primordial plasma that filled the early universe, and we were going to look at the differences between matter and antimatter to see whether they cast light on the origin of the matter in the universe. So around the ring there are 4 points where there are collisions, and around each one there is a detector. And these are pictures of the detectors while they're under construction. So the two biggest ones, Atlas and CMS, were the ones that discovered the Higgs boson and are now trying to find dark matter. LHCb is looking at the differences between matter and antimatter, maybe casting light on the origin of the matter in the universe. And this one here, Ellis, is studying the primordial plasma that filled the universe when it was a fraction of a second old. And I might mention that there are physicists from Ireland who participate in the CMS and the LHCb experiments. So on this map here, you see that although the experiments are done at CERN, they are done by physicists, thousands of physicists from over 100 different countries around the world, including, as I mentioned, Ireland. So these are the physicists whose institutes are in Ireland. You can also ask yourself, how many people working at CERN have Irish passports? Then it goes up to 14. So Ireland is a net exporter of particle physicists because, quite frankly, the opportunities for doing particle physics in Ireland are not so great. That's the end of the politics. Okay, so the efforts of these thousands of physicists led in 2012 to the discovery of the Higgs boson, an event which caused what I like to describe as mass Higgsteria in the particle physics community. So what was this Higgsteria caused by? It was caused by the Atlas and CMS experiments announcing the discovery of a new particle which behaved in a very distinctive way. And this is one example of that. So this is a computer reconstruction of a collision in the CMS experiment. So these yellow lines here, these are charged particles being produced in the collision and sort of wandering out through the magnetic field. Here you see a couple of red lines with no charged particle heading in their direction. And those are believed to be two energetic photons, which probably came from the decay of a Higgs boson, which was one of the processes that we calculated in our paper back in 1975. So there was a big presentation of the results in the CERN auditorium, lots of happy physicists, including Peter Higgs, whom you see here on the right-hand side. And here also is François Anclair, who proposed similar ideas around the same time. He didn't actually predict the boson, but he got the other features of the theory. And one of the things that I found amazing is that in the 48 years between the time when they proposed their theories and the discovery of the Higgs boson, they had never met. You're shaking your head? This is the instant when they met. I don't know how it's possible. Theoretical physicists at least used to travel around the world all the time, going to conferences and talking to each other. But anyway. And then over here, I've highlighted Fabiola Gianotti, who presented the results of the Atlas collaboration that day, and who is now the Director General of CERN. So it just goes to prove that there is no glass ceiling in particle physics. So what happened on that day was that the discovery of a new particle was announced. And it was discovered while people were looking for the Higgs boson. And it looked like a Higgs boson. But was it a Higgs boson, or was it some sort of an imposter? So it's a little bit like when you're doing a jigsaw puzzle. There's a piece missing. Finally, you find a piece of bent cardboard in the back of the sofa. The picture's been rubbed off. is this the missing piece? So that was one of the things that I was interested in exploring after this new particle was discovered. And I worked together with my then PhD student, and we analyzed the couplings of the Higgs boson to different particles. So since the Higgs boson gives masses to other particles, the connections with those other particles should be proportional to the mass. So that's what we wanted to check, and the answer is yes. Everything is consistent with the idea that this is indeed the Higgs boson. So in 2013, the Nobel Prize was given to Peter Higgs and François Englert, and their citation included the statement, "Today we believe that beyond any reasonable doubt, it is a Higgs boson." So my student and I were very happy because that quotation was taken from our paper. But what the Nobel Prize Committee did not know was that when we sent our paper to the journal said, "Beyond any reasonable doubt is not a scientific term. If you want to get your paper published, you have to take that expression out of your paper." So, beyond any reasonable doubt was good enough for the Nobel Prize Committee, but not for the journal. Never mind. Anyway, the existence of the Higgs boson is a big deal. Without it, there'd be no atoms, no heavy nuclei, life would be impossible, so big deal. So, what does particle physics do for an encore after the discovery of the Higgs boson? So I would follow James Bond in claiming that, well, he said the world is not enough. I think he had in mind one world rather than many worlds, but anyway, I argue that the standard model is not enough. And because he used to have the number 007, I give 007 reasons for thinking there must be physics beyond the standard model waiting there to be discovered. So one is that according to our calculations within the standard model, empty space is unstable. And I'll say what I mean by that in a moment. I already mentioned the problems of the nature of dark matter and the origin of matter. And there's several other problems to do with the size and age of the universe, finding a theory of quantum gravity. I'm not going to discuss those, although many of those other issues are also addressed by the LHC in some form or another. Instead, I'll just focus on these first three issues. So, if you calculate in the standard model, you find that there is probably an energy state with a very dense value of the Higgs field, which has a lower energy than our current state. And this is a problem because everything fluctuates according to quantum mechanics, and there is a non-zero probability that our universe would jump through into this ultra-dense state. If you calculate the rate at which that's going to happen, no, Putin will get us first. Come on, laugh up a little bit. But it's not that's not the only problem. There's a problem of how we got to be in this state in the first place, and why didn't the whole universe, or at least most of it, just go straight into this ultra-dense state? So we should follow the proposal of Donald Trump and erect a barrier to prevent us from falling into that big crunch state. To build a barrier, we need to postulate new physics beyond the standard model. And one example of that is supersymmetry. And I'll come back to supersymmetry in a moment because Lochlainn O'Raifeartaigh played a key role in developing the theory of supersymmetry. So when people ask me, well, what physics do you think there is beyond the standard model? I have to say that my heart is still devoted to supersymmetry, although my love for Susie has not yet been requited. I would actually argue that runs of the LHC have actually given us additional reasons for liking supersymmetry. I just mentioned the fact that it would stabilize empty space. It enabled us to calculate correctly what the mass of the Higgs boson would be. It predicted correctly that the Higgs boson should look much like what is predicted in the standard model. Supersymmetry also plays key roles in many other theories that I won't go into, but what is important for my argument is it is also a source of dark matter. So this is where I would like to pay homage to the work of Lochlainn O'Raifeartaigh. So he, of course, did many wonderful pieces of theoretical physics during his career. But many of the most famous works that he did were related to supersymmetry. And in particular, he's particularly well known for a paper where he showed how you could make different masses for ordinary particles and supersymmetric particles, which is kind of important because we haven't actually seen any supersymmetric particles yet. So for that, we should be grateful to Lochlainn O'Raifeartaigh. So according to supersymmetry, all the known particles over here on the left should have partner particles here on the right with their little twiddles. And these three over here are neutral supersymmetric particles, quite possibly stable, which could provide the dark matter. So what is this dark matter? So the Swiss astronomer Fritz Zwicky was looking at galaxies in the Coma cluster back in the 1930s. And he found something a bit weird. The galaxies were moving around each other too fast in the sense that they needed some centripetal force to hold them together, and the visible matter in that cluster was not enough to keep them together to prevent the cluster from blowing apart. So he said, well, there must be some additional source of gravitational field. There must be some additional matter, invisible, so-called dark matter. Now, I think for about 40 years, his idea didn't really catch on. And I think a key role in convincing the astrophysics community that dark matter was a reality was played by the astronomer Vera Rubin, whom you see at work here. And she is famous for observing the motions of stars in galaxies and finding a similar phenomenon, that they were orbiting around galaxies too fast, and you needed some additional gravitational field to hold the galaxies together. So that was in the 1970s. Subsequently, much more evidence in favor of dark matter has come from various different sources, but I won't go into the details. This is just one illustration of the sort of measurement that Vera Rubin made. So you have a visible galaxy, which is relatively small, but you can observe stars and gas orbiting around the galaxy. And you find that the velocity at which it orbits, in many cases, is roughly constant. Well, that's a surprise, because if all the matter was concentrated in the visible part of the galaxy, then the further away you are, the smaller the gravitational field, the slower the orbital speed. But it doesn't go down, it stays constant, and that tells you there must be additional, invisible, dark stuff distributed over a much larger volume than the visible galaxy. And maybe that dark matter is made of particles, and maybe those particles are supersymmetric particles, and maybe we can detect them at the LHC. So how do you detect a dark matter particle? It's dark, so it doesn't have electric charge, doesn't radiate. It doesn't have strong interactions. All its interactions are very weak. So your detector elements won't pick it up. But what the dark matter particle does carry is energy. And so what you can do is look at all the energy coming out into the different parts of your detector and see whether you can account for all of it or whether there's some missing energy. And this is a computer simulation, shows what could happen if you produce particles of dark matter. So you've got a bunch of energetic particles coming out on one side of the detector, but nothing much on the other side. And that missing energy could have been carried away by supersymmetric particles. So, sad to say, although there have been many searches for supersymmetric particles at the LHC, none have yet been seen. The LHC experiments, of course, look for a lot of other things as well, so there's a lot of other things that they haven't found as well. And so now the LHC is starting a new run, and experimentalists are trying various different strategies to look for supersymmetry or other possible physics beyond the standard model. Some of them are continuing the same sort of study that was done previously. Others are looking for corners of parameter space that haven't been explored. And some people are thinking about novel signatures of supersymmetry. So that was dark matter. How about the origin of the matter in the universe? So as I mentioned earlier on, antimatter, which is something which was predicted by Dirac back in the 1920s, was first discovered in the cosmic rays. And subsequently, it's turned into a topic of great interest to the general public, who maybe they watched Tom Hanks, or maybe they watched Star Trek. I'm sorry to say we can't make enough antimatter at CERN to blow up the Vatican or to power up the Starship Enterprise. I didn't say that about the Vatican. Instead, what we're interested in doing is to try to understand how and why matter and antimatter are slightly different, and whether this is why the universe mainly contains matter but not antimatter. So the point here is that back in the 1920s, when Dirac proposed the existence of antimatter, he said, well, you should have the same mass as regular matter, but you should have opposite internal properties, like, for example, opposite electric charge. And that's the case, for example, for the antiparticle of the electron, the positron, which was discovered in cosmic rays, and actually now is used in medical applications. So it came as a big surprise when experiments discovered that actually matter and antimatter don't have exactly equal and opposite interactions. And we don't have a fundamental theory of that. We have a description of it within the standard model, but we're still trying to understand where that difference comes from. And the Russian physicist Sakharov proposed in 1967 that small difference between matter and antimatter could be why there is more matter than antimatter produced in the Big Bang. Then the antimatter would all annihilate with particles of matter, and we'd be left with the matter that we see in the universe today. So that's a great idea, and as I mentioned, there's an experiment at CERN, also elsewhere, looking to see whether this theory holds water. Okay, so that brings me to the end of what I wanted to say. I hope I've convinced you that the LHC is not only the world's most powerful microscope looking at the intimate structure of matter, but it's also in some sense a super telescope which is capable of answering at least some of Gauguin's questions. What are we? Where do we come from? And maybe where are we going? Thank you.
Gur míle maith agat. floor is open to questions.
Thank you so much, John. You talked about how different particles get their masses. Thank you. You talked about how different particles get their masses through their interactions with the Higgs field, but you didn't talk about how the Higgs field itself gets its mass.
Yes, well, it gets itself from itself. It gets its mass from itself. And the way I like to think about it is it's one thing to have an isolated snowflake, but when we're considering the snowfield in Siberia, how does the snow manifest itself? It typically manifests itself in lumps of snow, snowballs, if you like. And these are due to self-interactions between the different snowflakes, and that generates a non-zero mass.
Thank you very much for a wonderful talk. One question I would have is, if I remember Lochlainn's original motivation as he wrote at the time for the whole sort of his interest in supersymmetry was to do with unification, that there were these theorems showing that you couldn't go any further with unified field theory along the lines people had been going, and that supersymmetry provided a way around it. If it's the case that, say, as the years progress, there's still no sign of maybe supersymmetric particles at the LHC, are there other ways of achieving unification of the fundamental interactions now without supersymmetry?
Okay, well, first just to reinforce a little bit of the historical message that you gave, I think that Lochlainn's perhaps deepest work, although perhaps it's not as famous as the work he did on supersymmetry, was he studied ways that people were trying at the time to make unified theories. And he actually proved that you couldn't combine the internal properties of particles and relativity in a non-trivial way. And for some reason, which I'm not quite sure, this has subsequently become known as the Coleman-Mandula theorem. But anyway, so he was interested in symmetries and unification, right from the beginning. This was his primary motivation. I agree. So indeed, supersymmetry seems to play a key role in string theory, which is, in my mind, the best candidate that we have for quantum theory of gravity. It's also true that supersymmetry seems to help you along the way to unification by bringing the strengths of the different types of interaction together in a nice way. But those are very, if you like, theoretical arguments. They're not empirical arguments. But they're still arguments that I like. Now, you could maybe unify without postulating supersymmetry by putting in some new physics beyond some different physics beyond the standard model. But string theorists will correct me if I'm wrong, but I think that nobody really knows how to make a consistent string theory which does not have supersymmetry.
Thanks for a great talk. I'm curious to know your take on low energy, high precision measurements or experiments. I mean, this morning you alluded to atomic clocks and interferometers. Do you think that those kind of low energy experiments will really be able to reveal physics beyond the standard model?
Yes, because if I didn't think that, then I wouldn't be participating in the experiments that do that or that try that. But I would caution that although low energy precision experiments can maybe tell you that there is some new physics out there, they can't always tell you what that physics is. It can maybe give you some clues as to what it might be. But eventually, if you really want to pin down what that new physics really is, you think you just need to go up to high energies. And I think an example of that is the weak interactions, where I discussed this in some detail this morning. You had a sort of empirical description of how weak interactions worked, but you didn't have a theory. You had to build the big accelerators and make the colliders and find the particles that actually generated the weak interactions. So they go hand in hand, but the low energy experiments are very important, but they're not going to provide all the answers.
Yeah, you mentioned there about the rotation curves of galaxies and how they might be Donald Trump walls in the universe. Hundreds of million light years across, all wrapped up together in diameter. But that is only 4% of the matter of the universe. So if you're saying that they're flowing along the snowflake Higgs boson field as they move in those tunnels or walls of Trump, then that's the circumference of a bubble they're on. So what I'm trying to figure out is, when you say a Higgs boson is on the circumference of these bubbles, can a Higgs boson go through the radius to the center on the far side, or is that totally different from what they're in?
Okay, well, the first comment that I would make is that indeed the visible matter in the universe is about 4% of the total energy density of the universe. Then there's something like another 25% or so which is in the form of dark matter. So I'm not sure that I understood every aspect of your question, but what we believe is that the dark matter is clumped around the visible matter, made it possible for the visible matter to hold together, if you like. But in addition to the dark matter and the regular matter, the remaining something like 2/3 or 70% is another sort of dark stuff, dark energy, which differs from dark matter in that it is not attractive gravitationally, but it's actually repulsive. So and that's present everywhere, also in the empty spaces that you were mentioning between the galaxies. And in fact, according to conventional cosmology, if that energy density remains constant, those voids will just get bigger and bigger and bigger, and the astronomers 100 billion years hence will basically not be able to see anything apart from our own local cluster of galaxies. Everything else would be what currently we would think of as a void.
Yes, thank you for the great talk. So you say that, according to you, like the best candidate so far is string theory for a unified theory. What is your take that we have a positive cosmological constant which points to a de Sitter universe, and there is, as far as I know, I'm not an expert of course, but there is no consistent way in the landscape to have a positive constant. I think you have like either a negative for an anti-de Sitter, or you have zero Minkowski. What is your hope that we can produce with this theory our universe? Thank you.
Okay. So maybe I'll just fill in a couple of details. So Einstein, of course, postulated the cosmological constant shortly after he postulated the theory of relativity. And he said cosmological constant, right? So the dark energy that I was talking about a moment ago may be constant or it may not be constant. Okay, so it looks kind of constant at the moment, but who knows whether that's going to persist. And if these arguments about the instability of empty space are correct, then in fact it will shift at some point in the future, in the distant future. So the dark energy is not necessarily a cosmological constant. So I sort of suspect that probably a lot of string theorists are kind of hoping that that's what's going to happen in a sense that the cosmological constant actually isn't constant, then dark energy will gradually go down to zero. I'd actually be quite happy if it stays non-zero. I mean, I agree that I presented to the gentleman at the back a somewhat bleak future where astronomy beyond our local cluster of galaxies will become impossible 100 billion years from now, but I'm not going to be around, so I can say that. I'm not convinced that it's really impossible to formulate string theory in a de Sitter background. And I've tried to develop some ideas about how that might be done, but that was a long time ago, and I wasn't able to push them through until the end, but it's still, deep in my soul, I believe it should be possible to put string theory in a de Sitter background.
As a metastable state, or do you think we can make actual predictions in this state? Like, we say that de Sitter is a phase and then we move to anti-de Sitter and we make predictions there, or do you think like...
Well, obviously, if you're in a de Sitter state, your ability to make predictions is limited, right? And I think we just have to accept that limitation. It's a little bit like what Faye was saying earlier on about quantum mechanics. You can't predict everything, and you must somehow give up on this overweening ambition to be in a position to predict everything. So I guess what I'm trying to say is, maybe the string theorists are being a little bit too ambitious, and if they're a little bit less ambitious, then they might actually succeed.
So first of all, thanks for an excellent talk, and I'm sorry, I want to bring you back to the Higgs boson again, and I'm wondering if you could share with us whatever intuition you might have about how we should think about the Higgs boson. So I'm not satisfied with your snowflake example. So is this in the mass of an electron, should we think of these Higgs bosons as somehow tightly wrapped inside of an electron, whizzing around inside an electron? Any intuition there? Should I think of it as are Higgs bosons all around us everywhere? Are we in a soup of Higgs bosons, or?
Well, don't worry. Real Higgs bosons aren't around you all the time. Every once in a while, a cosmic ray produces a real Higgs boson, but it decays too quickly for anybody ever to be able to observe it. So what we do have in what we call the vacuum is we have virtual particles that come into and out of existence. Okay, and the Higgs boson is among those. And in fact, we were able to predict the mass of the Higgs boson from its quantum effects before the thing was actually discovered. We were able to predict what the mass should be. So when you think of an electron, you should think of it as interacting with the Higgs field, which is on the one hand a classical field, which is just there, but it's also a quantum field with which it interacts. It comes in and out of existence. It's not there all the time, but statistically it's appearing and disappearing.
Is it like a gravitational field? Or?
Well, so there are similar phenomena with the gravitational field, although there are differences. I described some of them. Gravitational fields have sources, and that classically the gravitational field is not constant throughout the universe, whereas the Higgs field apparently is constant. But the other processes, are kind of similar in the sense that, gravitational fields deviate the trajectories of particles. There are quantum gravitational effects, which we find difficult to calculate if we don't have string theory, and so on. I don't think that was a very satisfactory answer. But it's getting a little bit late in the evening. So.
Perhaps we should close the session.
Well, I'm happy to take
Maybe one more question.
One more question, if anybody...
John gave the lecture this morning at 9 a.m. So, and it's approaching 9 p.m. So we have to take that into consideration. So let's take one last question.
Hi, John. Nice talk. I'm just wondering if you have a hope that the electron-ion collider will exploit the spin degree of freedom there to possibly show what future theories might look like.
Sorry, I didn't quite...
I'm just thinking of the electron-ion collider that's being built in the States now.
Oh, the electron-ion collider. Well, I'm sorry to disappoint you, but I don't think this is going to add any new fields or particles to put on the T-shirt. I think that's going to be a wonderful machine for understanding the way that protons are put together, the way that quarks are held together by particles called gluons that I didn't mention, but you know all about them. I think it's going to be wonderful for doing that, but I don't think it's going to, as I said, discover any new particles for us.
Okay, I think we should thank both speakers for and thank you all for coming.